Yeah, so you've already heard a little bit about contract theory. Pierre mentioned some aspects in his lectures. There was already one talk yesterday that mentioned that. So what I would like to do here is give you a little bit of an overview of what the problems are, what we can do. I won't have time to go in details in the proof, so it's going to be mostly intuitive. And there will most likely be enough time for me to also make links with mean field games and mean field type control, which are things that can actually show up naturally in some of those contract theory problems. Right, so the first thing I want to tell you about is going to be non-continuous time problems. We're just going to look at a static version of the problem, simply because there I can introduce all the definitions. Things are quite clear. You can define the problems. You cannot solve them in general. That's why we're going to have to move to continuous time. But in order to understand what's going on, static versions are plenty enough. All right? So what's going on there? So the typical problem you want to have a look at, this is going to involve two participants. One of them we will call the principal. So the tradition in that literature is that the principal is female, so I will try to remember to call the principal she. And so what principal does is she wants to hire someone to do something. So I'm on purpose very vague here, because basically this is any type of situation where there is some sort of contract happening between two persons. That can be principal hire someone to work on a project. That can be the principal actually taking someone else as a client, and there is like exchange of services going on there. There are many, many situations. I'll have the opportunity to give you some examples later on. And then you have another one, agent. That's the person to be hired in order to do something. So really, if you want to have like an example that's going to guide you through everything, think of the simplest possible situation. Principal wants to hire someone to perform a task. That person is the agent, and the agent is going to be compensated for doing the task. So the question is how the agent should be compensated for the task. Now, the way you're going to set that up is going to depend a lot on what you assume, what type of information you assume is available to everyone. I will talk mainly about two situations. One where everyone knows everything, meaning that I will be able, if I'm the principal, I will be able to check exactly what the agent is doing. I tell the agent, please do this for me, but it's like I'm behind his back and checking everything that he's doing. So that would be a case where you have full information. And in that case, the contracting problem is going to be different from another case where you might have some information that is not available to you concerning the agent. And typically, in our case, we will consider the situation where I don't know exactly what the agent is doing. I know he's performing the task. I know he's working. I don't know how much work he's actually making. I see the result in the end, but I have no way of knowing whether if I'm seeing good results, that's because the agent did a good job, or he was maybe just lucky. And if I see poor results, I cannot be completely sure whether that's actually because it didn't work at all or it just got unlucky. Okay? It's a typical situation when you have PhD students, you leave them away for a month, they come back, you see things, you don't really know what happened there, whether it's good or bad. So that's really exactly what's going on there. So here, this depends fundamentally on the information available to both parties. So this question of having potentially asymmetry of information, this is really what drove in the beginning economists to start looking into this. So I would say that the first studies about this, serious ones, probably date back to the 50s, maybe a little bit more in the 60s and 70s, but you already have works there. That was mostly static models, some discrete time ones. The continuous time versions of all of this started in the end of the 80s, beginning of the 90s. And you will see why there is a little gap later on, because the theory in the static case is very nice, but it doesn't take you very far, in the sense that the assumptions that you need to make in order to be able to say anything about the problem are too strong for practical applications in most cases. All right, so that's probably still a bit vague, so let me show you what the basic models look like. So what I need here at this stage is we give ourselves some measurable space. In which we have some random variable that I'm going to call x. And this x is what we will call the output. That is the result of whatever task the agent is performing. So if you want, maybe you're hiring the agent to manage a project, and X is just the value associated to that project once the contracting period is over. So typically here, the principal will set up a contract at time 0. Okay, so I'm in a static setting. There will be only two times, 0 and 1. So the principal sets up a contract at time 0. What is to say he chooses, let's say, a Borel measurable map psi. I'm taking from R to R. So here I'm just take this guy real valued. Can be multidimensional, that doesn't change much about the presentation here, but let's just take it real valued for now. And that just means that the payment at time 1, this is this. All right, so there will be some uncertainty about the realization of X. This will be resolved at time 1. The principal doesn't know that in advance, but it's just telling the agent, we're going to see what happens at time 1. Depending on the result of the work that you have done, this is the salary you will get. Right? So this, for instance, could be if we say X is the value of the project. If X is above a certain threshold, you get that amount. If X is below that threshold, you get another amount. You're just fixing the rule here about what's going on. And a priori, yeah, I just need a little bit of measurability so that the problem makes sense at this stage. All right, so that's how the principal is going to do, is going to choose this functional here, observe X, and pay that to the agent. Now, what does the agent do? So here what we have is something that Pierre mentioned above. So we have two players in this game here, the principal and the agent, and we will be looking for some sort of equilibrium, except it's not going to be Nash, it's going to be a Stackelberg equilibrium, because there is an order in which the players are playing. The principal plays first. He says, this is the contract. Agent says, okay, that's how much I'm going to be paid. Observing that is going to decide how much effort is going to put into the problem. I'm going to show you in a second how he decides what that effort is going to be. But that's this, and because the principal is playing first, he has more power in the game, in the sense that he can anticipate the reaction that the agent is going to have to a given contract, and then use this in feedback. And yeah, so in those games where you have an order, like a clear order in which the players are playing, one reasonable notion that you can look for is Nash Equilibrium. So in game theory, this is also called leader-follower games, simply because here the principal is leading, playing first by offering a contract, and the agent is following, given the contract, is going to choose an effort. So how does this work, the efforts? So now given a contract, so he needs to choose an effort, and here again, I'm going to take something very simple. The rule about the contract is announced at time 0. So at time 0, the agent knows how he's going to get paid. He doesn't know exactly how much is going to be paid because we don't know yet what the value of X is. But he knows how to compute it given that he has access to it. So what we will do here, this is just choosing some number A in R, and he chooses this at time 0. Again, I'm taking one-dimensional efforts. Nothing changed fundamentally if you take efforts that are multidimensional. And if you move to continuous time, you can actually sometimes take efforts valued in some like appropriate Polish space. It doesn't change too much about the theory, the general part at least. Okay, so now how does all of this work? So what we assume is that any choice of effort A is going to generate a probability measure on our measurable space. All right, and well, this is supposed to give me information about the random variable x. And the assumption here in the simplest versions of the model is that under PA, x is going to have a continuous distribution with density some f that depends on A. So let me give you an example so that you see a little bit clearly what I mean there. So one typical example would be that under PA, x is distributed as a Gaussian random variable with mean A and variance sigma squared, right? Which just means that I take for f of x and A the Gaussian density, so exponential minus xa squared over 2 sigma squared square root 2 pi sigma. Okay, so what's the interpretation in a case like that? So here, instead of x being the value of the project, because it can take negative values here, maybe it's better to interpret it as benefits associated to the project. So they can be either positive or negative. There is some idiosyncratic noise, sigma squared here, okay, which is basically whatever your economic environment, whatever impact it has on the project that you cannot control yourself. So maybe your project is actually doing great because the environment is good, like you're back a little bit before the 2000s and you are doing a startup connected to whatever internet, and even if it's crap, it's going to have a huge value. And that's not because what you're doing is good, that's just because the environment is pushing this up. And you can be just after the crisis, and if you do something very good, the value has decreased. So this is just captured in a very stylized way by whatever you have sigma squared here. And then, of course, there is the effort of the agent. So the more effort the agent makes, the higher A is, then on average, the higher the value of the benefits are. All right, so the agent can put work into there in order to, well, give an average value here that is potentially higher. Okay, but of course, there are things that he cannot control that are due to the variance here. Okay, so that's a good example because you will see that everything that I will show you in the static case doesn't work for that example. So it looks extremely simple, but the static case cannot cover that. I mean, we can solve the problem, but the solution is not very satisfactory. While when we're going to move to continuous time, this is going to be all nice and clean. The equivalent of the Gaussian distribution here would be Brownian diffusions, and the agent would be choosing the drift associated here, and it will be facing some Brownian motion with a volatility sigma there. All right, but so that's the example. Now, okay, we know that the agent is choosing an effort, it generates a probability measure, so it generates a distribution for the output. How does it choose the effort A? Well, it's going to be a utility maximizer. And there are, say, mainly two specifications in that literature. So this is what I call the utility that the agent gets when he receives contract xi. So that's the payment he receives. That's the effort he's choosing. So this will be, let me give you the two specifications. So one would be the average under the measure associated to A here of, say, some utility of the payment that he receives here. Minus C here, and what is this? This is a cost function. Right, so this is the cost of making effort A for the agent. And he just has, as an expected utility maximizer, at time 1, he receives this, he evaluates this with its utility function, and then takes the average. Another case that's also useful, so that's a specific choice of the utility function. So it's the case where the agent has exponential utility, and in this case it's usually better to actually put the cost inside the utility. Right, so this, the first case is what people would usually call additively separable, because I have additive separability between the utility of payment and the cost of effort, while this one is multiplicatively separable, because it's an exponential, so I can actually separate those two guys. And I have multiplicative separability between utility of payment and cost. I can do things for a more general class that I think they call quasi-separable utility functions, that kind of covers both of those here, but that's not that important at this stage, but you can do a little bit better. Again, this dichotomy that I'm showing here, you see it again in the continuous time models where I am not going to be able to do whatever I want for the agent's problem. All right, so that's the utility of the agent, and what the agent does he wants to solve the problem of maximizing over efforts his utility given a contract that's been offered to him. When the principal comes and says, I'm going to pay you that, the agent says, okay, then how do I choose my effort? By solving this optimization problem here. Okay, now what I need to understand is what does the principal do? How does the principal choose the contract? Well, same thing, principal is going to be a utility maximizer. And then we define, again, the utility that the principal gets when he offers this contract and the agent makes this level of effort. I'm going to be given some utility function for the principal and very simple specification here. principal has his own utility function, and he gets utility from what? We assume here that the value that he gets from the project is just x by itself, and he's getting this utility by having to pay the salary to the agent. You can change that completely. I mean, you can put whatever functional you want here of x and xi. That's not going to change much. It's just that this one would be the most classical one. You just expect that this is wealth that the principal gets, and you just get the net wealth by subtracting the payment that he makes at time 1. All right. So that's kind of setting up the problem there. We know how everybody computes his or her utility. Now, what is the problem that the principal solves? And here, the problem that he's facing is going to depend, as I, yes?
It's just not inside here, the bottleneck with the left on R to R. I think this would be the leader from R.
X is R valued.
No, X, xi.
But X is R valued, and xi is a function of X. Yeah, I haven't written it yet. Thank you. You're right. Xi is a function of X. It's implicit in everything I write, but you're completely right. I should be writing it as explicitly as a function of the observation. Okay, so now the question is that the problem faced by the principal that depends on her available information. So we're going to check the two cases I mentioned a bit earlier. So the one where principal has all information, and the case where the principal observes X but has no access to the effort that the agent is making, so principal doesn't know A. So the first case would be principal knows X and A, and the second case will be the one where principal only knows X. That must be 2. So this is what I will call the first best case, where you have full information. So here we assume the principal knows both X and A. So in this case, there is nothing in principle that prevents the principal to use the value of A in the contract. So you could start thinking that it's valid in this case to offer a contract that says, all right, so I will be monitoring you. I will know exactly what you're doing. If you do that level of effort, you receive 10 euros. If you do anything else, you owe me 1,000 euros. Okay? That would be in principle a valid contract. Now the agent looks at this and says, okay, well, obviously for me the best thing to do is to work the amount that the principal has asked me to work, because otherwise I owe him money. Her money. So what this means is that in a setting like that, what you should assume is that principal is actually choosing both X and A. He's telling to the agent, this is how much I'm going to pay you, and this is how much you're going to work, and the agent has no choice. He will have a choice in terms of whether he accepts or refuses the contract, but once the contract is accepted, he will perform exactly the amount of effort that the principal wants, and he will receive exactly the amount of money that the principal wants. So in this case, what the principle will do is, so I will call this V0P first best. That's what the FB means here. So this will be the sup over A and Xi. Okay, so now my contracts here, I put them in some set calligraphic C. I will say something about that in a second, but I don't want to go into details about what this should be. But in any case, the problem that he's solving is this one. It's maximizing over both of these things is utility. So that was x minus xi of x. All right? If I only write this, the problem is kind of trivial. I don't pay anything to the agent. I actually ask him for money, and I make him work as much as possible. So if I just put this, the problem is going to be degenerate automatically. So if you want to avoid that, we're going to add a constraint here. And the constraint is that, put it like this, with the amount of effort that I ask the agent to perform and the payment that I will give him, this utility is lower bounded by some value R, which is called the reservation utility. And this constraint here is usually called the IR constraint for individual rationality. So the point is just that agent says, okay, I will do what you tell me, but I will only accept contracts such that I at least get this amount of utility. Because maybe this is what I can get from a competitor. So if you don't give me at least that, I don't accept the contract. So you just encode this in the problem of the principle by saying that the contracts and the efforts chosen have to satisfy this here, which is a participation constraint from the point of view of the agent. All right? So if you look at this, I mean, I need to tell you a little bit more about C, but at this stage what you have is an optimization problem. This is a utility function, so it's going to be typically concave. So it's a concave optimization problem with a constraint here that's a nice linear constraint, right? Simply because this V here is an expectation of something. It's just a linear constraint. So, well, you know what you're going to do with something like that. It's classical convex optimization for static problems. And what you would naturally do is look at the dual value of the problem, write the Lagrange multiplier, expect that strong duality holds, and you can solve the problem that way. So this is where, if you want to make these things rigorous, I need to tell you a little bit about what C is. So what you would typically do depends on which field you are. If you're an economist, you just say, yeah, I write first order conditions with respect to Xi, which is a function also. In principle, you should put it in a nice Banach space where you have a notion of differentiability and try to make sense of all of that properly. They tend to not bother with those details. And if you have more of a mathematical background, then you try to write down correct proofs. But the results are the same in the end. It's just one of them takes you a little bit longer because you want to write it properly. But let me just show you what type of intuitions you can get from solving those problems in the two cases I showed you for the specification of VA, because that tells you already what typical shapes of contracts you should expect. You can already see that at that level. So this here, as I said, this is a standard. Convex optimization problem. So you introduce the Lagrangian here, which would be some L that depends on psi, on A, and some Lagrange multiplier lambda, which is just at this stage, so with my notation, that would be V0P of psi and A plus lambda V0A minus R. Okay, and then, well, if strong duality holds, you know that solving the constraint problem here is the same as taking the inf over Lagrange multipliers of the sup over psi and A of this quantity here. Okay? So typically you would have that V0P FB is just the inf over the Lagrange multipliers sup here of M. Right, and if you want to prove that this is true and there is no duality gap, that's typically where I need a little bit of topological structure on C. The main results, even if you're in infinite dimensions, you need non-vector spaces at least. So yeah, like the typical thing would be to take for C spaces of random variables with certain integrability. You can take L2, for instance, if that works in the problem. You can take more complicated things. That doesn't really matter. The point is that that's how you will solve the problem in general. And in continuous time, the exact equivalent of this would be to use convex duality techniques. That still works in many different cases. The important point for me is just, let's stay at the intuitive level and look at what the first order conditions with respect to psi, what do they give you? So let me just put this in a remark, because I'm not going to do more than that for this problem. So, yeah. So intuitively, I'm just going to put differentiating with respect to psi. So I put differentiating again because, well, if I don't put some Banach structure in which I can define Fréchet or Gateau derivatives, what I'm saying doesn't make much sense. But that doesn't change much. So let's say that we can do that. And if you go back to the additively separable case, so that's the one where V0A here is just expectation of utility of psi minus the cost with the cost outside. If you do the computations here, you will get that this should lead you to the following. So if I didn't make a mistake, let me just check. Yeah, that's correct. So if you do the computations in that case, you will see that, again, you have something that's nice and concave in psi, so first order conditions should be sufficient. So this should characterize the optimal contract. And what you see here is that the ratio of marginal utilities for the principal and the agent, so those are marginal utilities because they are derivatives of the utilities, at equilibrium, the ratio of marginal utilities is constant. So if you've done a little bit of microeconomic theory, this is a standard result at equilibrium, that ratio of marginal prices, ratios of marginal utilities tends to be constant, right? This is exactly what's happening here. And this is called the Borch rule, because that was first observed in a paper by Borch sometime in the 70s, that says that the ratio of marginal utilities is constant at equilibrium. Something that might be a little bit more interesting here is the case where the principal is risk neutral. So principal risk neutral means that his utility function is an affine function, in which case the derivative here is a constant. So this becomes a constant, and here what this is telling me is that 1 over u prime a of psi is a constant. Well, if the utility function here is nice and increasing, yeah, no, it needs to be strictly concave. If it's strictly concave, then I can invert the relationship, and it's actually telling me that the optimal contract is constant. So here in particular, so you have a risk neutral principle, then psi should be u prime a minus 1 of 1 over lambda. The value itself is not important. What is important is that this is constant. So that's telling you that in the case where the principal is risk neutral and it has full information, what payment do you make? You make constant payment. It's a fixed salary. You just tell the agent, yeah, whatever you do, I mean, I'm the one choosing how much work you're going to put there, but I will pay you a constant salary. So if you do the same computations in the multiplicatively separable case, so in this case, that was the one where the agent had exponential utility. If the principal also has exponential utility, okay, so his utility is like this. The risk aversion that he has may be different from that of the agent, but if they both have exponential utilities, you can do exactly the same computations, and you will find that again, first order conditions will lead you this time to psi being equal to some constant plus yes. So this time you have a fixed part exactly as before, but there is also a part of your salary that's indexed on X. And this here, so again, you have the part that is whatever you will always get that one here, but when you look at the quantity here, you do get some sort of sharing of the risks associated with the project, because both the agent and the principal are going to be sharing that part here of X. And of course, when gamma p is 0 and the agent is risk neutral, this becomes 0 again. So this is like a variable part in your salary, which is indexed on performance, because basically if you're thinking of X as being benefits of the project, what the contract is saying is that the agent is getting a share given by this ratio here of the benefits. So already in those very simple models, you see some features from real life contracts where you have fixed and bonus parts here. The fact that this is linear, of course, I mean that the dependence here is linear with respect to X comes from the specification of exponential utilities. But yeah, so you already see these type of things showing up. All right. So is everything clear until now? So I just wanted to show you examples. Again, this is an extremely classical problem once you get to what the principle is solving is convex optimization. I don't need to tell you much more about that. That's relatively easy to solve afterwards. Things become more interesting, of course, when there is actual asymmetry of information, and the only thing that the principle observes is X and not A. And there the problem becomes much more complicated. So now the next question is what happens now does not observe efforts made by the agent. So now this is the case that's usually called second best, or also moral hazard. So moral hazard that comes from the fact that because the principal doesn't know what effort the agent is making, there is a possibility that the efforts that the agent is going to make is going to be more than suboptimal. It could have like negative effects on what the principal wants. But he has no way of controlling this directly. So that's why you get this moral hazard component that shows up here. So this is something that started mostly in the insurance literature, because that's the typical case where, well, you're insuring someone for health, obviously it's bad for you when that person is behaving recklessly and they do skydiving, or they go out during the winter without proper clothing, they get sick, and then you have to pay for that. But there is no way that you're going to force them to, I mean, skydiving you could by telling them that this is not covered in the insurance, but going outside of their home without proper clothing where it's cold, or not wearing face masks during a pandemic, there is no way you can enforce that directly. So that's where the name comes from. So what do we do in this case? You have again not again, but you have two ways of writing down the problem. There is the one that's, that people in the economics literature do. That's not my favorite. And then there is the other one that I like more, but they're both completely equivalent. It's just that the story is longer to tell in one formulation. But let me still give you both of them. So the first formulation, the story is that the principal cannot make the agent do whatever effort that she wants, but she can recommend a level of effort. So principal can come to the agent and say, look, this is how much I will pay you, that's the contract, and I strongly recommend, but I cannot force you, that you do this level of effort. The agent is going to say, okay, going to look at the salary that he's getting, and how does he choose his effort? He's going to optimize his own utility. And when will he follow the recommendation of the principal? Well, he will follow the recommendation of the principal if and only if he realizes that, oh, if I follow the recommendation, I cannot get more utility. So he will follow the recommendation if and only if that recommendation of effort is in the argmax of his own optimization problem. Right? Because if you say, do this, and he realizes by doing something else he gets strictly more utility, there is no reason why you would follow the recommendation. So when I'm saying this, I am implicitly assuming that the agent is nice, in the sense that if he does realize that he cannot improve his utility, he will follow the recommendation. You could have the cases where maybe the argmax is not a singleton, and there are maybe several maximizers. The principal is telling him, please do this one, and he's like, yeah, no, I'd rather do the other one. I get the same utility, but I don't like you, so I don't want to follow the recommendation. So in that setting, you assume that no. When the agent is indifferent between two efforts, he does whatever the principal tells him to do. Okay? So this becomes much more complicated. So this is kind of innocuous when I have one principal and one agent. I will tell you at some point about what happens when you have one principal and several agents interacting with one another. When the agents interact and you're looking for Nash equilibria between the agents, the fact that there are several Nash equilibria, that becomes complicated because you have no clear way of deciding, well, which one should we choose. And in this case, typically the agents are not going to be indifferent between the different equilibria. And unless you have a nice one that somehow dominates the others, like Pareto dominates the other, there is no, I mean, I have no clue how to choose it properly. So that's for later, but just keeping in mind that the assumption we make here is nice when you have one agent, not so nice when you think about more. Okay, so let me write this down. So in the first formulation, This one I call V0P. And what is V0P? So again, I suppose that the agent, the principal, maximizes over effort and contract. So here that's V0P aix-marseille. I still have the constraint that the utility that the agent gets is above the reservation utility. And then I have the additional constraint that I mentioned. This can only be a recommendation of effort. And the agent will follow that recommendation if and only if the effort is in the argmax for that given contract. So this is an additional constraint. That's called IC for incentive compatibility. And it's just saying that, yes, the principal is allowed to maximize over efforts, but given a contract psi, the only ones is allowed to consider are the ones which are maximizers for the utility of the agent for that given contract. So when you write the problem that way, well, you see clearly that the value here is in general lower than the value in the first best, simply because same criterion, this constraint is in both of them, and I'm adding an additional constraint here, so the set of feasible values here is smaller, so in principle, I get less. The other way of writing it is completely equivalent, but it's somehow more convenient in continuous time, the second one. So I can define what I will call A star of psi. So what is this? That's exactly the argmax. Right, so those are, for a given contract psi, all the efforts that maximize the utility of the agent. Okay? And then we can write also that V0P is exactly equal now to the sup over contracts, then the sup over efforts that are in this set, so efforts that are incentive compatible with the contract, meaning efforts which maximize the utility of the agent for that contract. All right, so when I do this, I just took the IC constraint here and I encoded it immediately in my criteria. It's just rewriting things down. There is no difference at all between both of them. But again, yeah, this is going to be easier to deal with in continuous time, even if both of them are completely equivalent. All right, so yes, I still need the other one. I still need IR here. Thank you. Okay, so that's what the problem looks like. Now the question is, what can I do with this? So there are several natural things you may wonder about the problem. First, you should realize that it's significantly more complicated than the previous one, because the constraint that we added is not one constraint, right? Typically, what I have here is like an infinite dimensional constraint, because checking that A is in the argmax supposedly involves me comparing the value at A with uncountably many other values, all right? So I cannot just put a Lagrange multiplier and deal with that. I have to think of something else to deal with that constraint. But before that, so one natural question that people have asked themselves is, okay, I just write this program. Can I find an optimal contract? Can I at least have some sort of abstract existence result that will tell me that optimal contract exists here? So I'm not going to show you anything related to that, just some references. So there is a line of research that's still active, and the best result I'm aware of is from 2017 about this. So the first one is do optimal contracts exist. So typical proofs here, what they do is, first, they need to restrict contracts, so you need to say a little bit more about the set C. I need to have nice topological structure there, typically. Most results also require lower bounds on salaries, so I don't necessarily have to assume that the salary is non-negative, but at least it has to be bounded from below. And then you just, if you put the right topological structure, this is the usual thing. You try to get compactness in one way or another and have an abstract result that tells you that a sufficiently continuous functional that you maximize over a compact set, the soup is attained. So most of the results there, you have papers by Page Jr. from the 90s. They are different but related. Now there is one paper by Carlier and Dana. So that one is in the 2000s, I think. So Guillaume Carlier has several results in that area. Most of them are related to another of those problems, which is called the adverse selection problem, where the asymmetry of information doesn't come from the fact that the principal doesn't see the efforts of the agent. It comes from the fact that the principal doesn't see some characteristics of the agent. So maybe the principal doesn't know the cost function of the agent. Maybe the principal doesn't know if the agent has exponential utility, maybe principal doesn't know the risk aversion. So principal typically has then a prior on the distribution in the population of that risk aversion or the cost function. And yeah, the problem is also more complicated. So in that area, there are plenty of results that are typically linked to optimal transport. The fact that those two things are linked, this is something that Ivar Eklund observed. Ivar says that Rocher saw it first, but he was the first one to kind of write it down clearly. And there are plenty of existence results you can get, but with the moral hazard, I think there's just one paper here that they did. And as I mentioned, the most recent one is by Kadan, Jewett, and Swinkles. Extremely general paper from 2017, where they show that, yeah, like under reasonable assumptions, let's say, that like the problem is way more general than the one I've written, you can have existence of randomized optimal contracts. So the typical result is that there needs to be some sort of randomization to make sure that existence occurs, and they have sufficient conditions under which you can actually have a pure optimal contract that exists. So these are things that are exist. The problem is that typically those results tell you, yes, there is an optimal contract, but they tell you nothing about it. They don't tell you how to compute it. They don't tell you any properties that the contract may have. So if you're interested in properties of the contract, so this is typically not enough to just have existence. So there used to be, because there are more recent results now, but there used to be basically just two approaches. One is due to Grossman and Hart, and that's one of the reasons why Hart got the Nobel Prize in economics. So my problem is the IC constraint, and I told you the problem is that, in general, that constraint is infinite dimensional. Well, what Grossman and Hart do is say, okay, well, it's infinite dimensional because I assume that I have infinitely many, uncountably many possible values for efforts. So they just say, okay, let's take cases where X has actually a discrete distribution, can take only finitely many values. Let's assume that there are only finitely many possible efforts, and let's try to solve the problem in that setting. So if you do those assumptions, you can solve everything completely and show that under reasonable assumption, you go back to standard convex optimization again. So I think the paper is from 83. Probably something like that. Yeah. So it's a typical thing when the state space that you have becomes finite, things tend to be a little bit easier. So finite state space and action. So when I say everything can be solved, and you can write down mathematical characterizations, if you want to compute things, well, obviously, if now your state space is big and the number of actions that you have is big, it becomes relatively impractical to compute anything at the end of the day, right? So mathematically speaking, that works perfectly well. It's just that in terms of computations, that doesn't help you much. That remark is also going to apply to things that I'm going to do in continuous time at the end. So it's not a criticism that I'm making there. It's just that when things become very highly dimensional, sometimes the math is beautiful and works well, but the numerics leave you in a place where you don't really know what to do. Anyway, so that's what they do here. And then there is another approach that's called the first order approach. And this says, well, the constraint IC is bothering me. I don't know what to do with this in general. So let's try to simplify it. So I'm assuming that something is in the argmax of this V0A here. If I were to know that the argmax here is an interior maximizer, then I would know that a necessary condition that the argmax has to satisfy is that the gradient at A should be 0 and that the second order derivative at A should be negative. What the first order approach does is to say, I am going to replace IC by just saying that the gradient of the utility of the agent at A is 0. So I replace this global optimality condition here by worse than a local optimality condition. I'm just putting first order conditions. So here the idea is to replace by something that I will call LIC for local IC, which is just that the derivative with respect to A of this at A is 0. Now, of course, assuming that I can do that, which means that this problem with this constraint and this problem with the new constraint have the same solutions, then I like this problem a lot, because now the complicated constraint that was here has just been replaced by an equality constraint. So I'm back to classical convex optimization. I have a convex problem and then I have one inequality constraint and one equality constraint. So I can write down KKT conditions for this and just try to study the solutions. Of course, the big gap in my reasoning is that is it true that the two problems have the same solutions? And if it's not true in general, which we should expect, can I give sufficient conditions under which the problems give you the same solutions? So yeah, that's where things become complicated, in the sense that first, it's extremely easy to come up with examples where the two problems have like widely different solutions. I think the first one is from 75 or something like that by Mirlis, where you can compute things by hand and you see clearly that, yeah, that's clearly not going to work in general. Then you have a series of results by many different people that give sufficient conditions under which the equality is true, but those sufficient conditions tend to, they're extremely strong in the sense that they eliminate many possible distributions, many classical distributions for X. So typically the Gaussian density for X that I gave you earlier never satisfies any of the sufficient conditions that exist in the literature. So I don't have time to show you this, but for this, what people call the validity of the first order approach, there is again a recent paper, 2017, from an economist in Canada called Kierkegaard. That has, I mean, the way it does it is beautiful, because somehow there are a certain number of isolated results, like you get sets of conditions. Okay, if you assume this, this works. If you assume that, this works. But there were no clear understanding of how those conditions were related to one another. And what Kierkegaard did is different approach, but which unifies all the existing sufficient conditions. And you realize that getting one instead of the other amounts to, so the whole thing that he does is that he shows that local IC being equivalent to IC can be recasted into a random variable dominating, I mean, a distribution dominating another distribution for some stochastic order. And getting some set of conditions means that you're using this stochastic order. Getting another one is because you're using another stochastic order. So I'm going to give you a couple of examples, but the most well-known ones are due to Rogerson, which at the end of the day means that Rogerson was using first-order stochastic dominance. Another one is due to Jewitt, and Jewitt was using second-order stochastic dominance. But before Kierkegaard's paper, it was no one knew how the two conditions were related to one another. Of course, if you know about stochastic order, you know that there are infinitely many of those that you can use. And any choice of a stochastic order generates another set of sufficient conditions. So it's great, but it's, in practice, it's useless because, again, whatever choice you're making, the typical constraint that this puts on the problem makes it that it's not, you cannot use it for any interesting problems. So you have plenty of papers in the economics literature where they assume first-order approach is valid. They deduce many things about optimal contracts, but the first-order approach is not valid in their context. So they're getting some contract that's not, it's not even clear that it's optimal, because if you only assume that, nothing is preventing you from having a saddle point. Nothing is preventing you to have actually a local minima instead of a local maxima. So any conclusion that you would get from this without being 100% sure that first-order approach is valid should be somehow taken with a lot of caution. Okay? Yeah, you have some time. So let me just give you a little bit of literature there, and I'm not going to spend more time, but yeah, the point is really that this doesn't work very well. Mathematically speaking, the results are very, I mean, they're beautiful, the theory is extremely nice to see, but practically speaking, that doesn't help you much. So here, the validity so this is typically a complicated problem. Requiring very strong assumptions. So the main reference is there. So there's this paper by Rogerson in '85. So what he assumes is what's called MLRP, for monotone likelihood ratio property. And this says what? I just need to check if it's increasing or decreasing, because I always forget. Yes. So this is asking you that the map that takes X and associates what you will call the monotone likelihood ratio. The likelihood ratio, so that's it's basically the derivative with respect to effort of the logarithm of the density. So if this is increasing, so that's the condition. So that's a relatively nice condition. I mean, most of the densities you can come up with will satisfy this, so that one is not too annoying. The one that's annoying is called CDFC for convexity something. So this one is asking that the second order derivative with respect to A of so not the density, the distribution function of F is greater than 0. So this should be a convex function. That one is a bad assumption. There are not many distributions out there that do satisfy this. So there is one paper by Dispasi and someone else, I don't remember the name, where they actually give a list of distributions that satisfies those things. But yeah, so Gaussian density doesn't satisfy that, for instance. So if you have those two conditions, then first order approach is valid, for instance. As I said, there is also this paper by Jewett, so that one is from '88. So Jewett is assuming what? So he's relaxing that condition, okay? And relaxing that condition means that is asking that what is convex is not this integral, this would be the integral of this with respect to x. So you get like a double integral, and that double integral should be the one that's convex. And you can actually keep going, so this here is related to first order stochastic dominance, as I mentioned. When you take the double integral, that's related to second order stochastic dominance. And if you keep adding integrals there, you get higher in stochastic dominance. So it's just asking for less and less about convexity, but what you're paying is what's going on here. And basically this assumption here is related to what? It's related to you need to have UA of psi star. So psi star is the optimizer in the problem where you've replaced IC by local AC. So I assume that that guy exists, is an interior maximizer, and I know how to characterize it. The actual condition that you need here is that this is non-decreasing with respect to x, and it's actually not too hard to show that MLRP is a sufficient condition for this to be non-decreasing. If I want to move to second order stochastic dominance here, if you again know about these things, this being non-decreasing will not be enough. I need it to be non-decreasing and concave, so then I need more things, and then if you keep going higher with stochastic dominance, then if I put a triple integral here, I need that thing to have first order derivative positive, second order derivative negative, third order derivative positive, so you get this alternance of signs here. So at the end of the day, what you're doing is relaxing this one, strengthening that one, or going the other way around. But yeah, you cannot really go much more outside of this. If I want to be thorough with references, another important paper here is by Conlon. That's 2009. So if you remember in the beginning, I told you that yeah, for simplicity, I take everything R-valued. For first order approach, this is not innocuous at all. It is excessively harder to treat the cases with this approach where X is multidimensional and where efforts are also taking values in multidimensional spaces. So Conlon has generalizations of the results in Rogerson and Jewett that also work in the multidimensional case. And then you have this result by Kierkegaard. That's again 2017, I think. That just unifies everything. It also works in the multidimensional case. It covers all the results that were existing before. It just explains to you where those sufficient conditions come from, generically speaking, but doesn't make the problem easier to deal with, again, because they're almost always too restrictive. So the good thing about the continuous time approach I'm going to show you this afternoon is that provided I write the problem properly in the beginning, it works regardless of the dimensions of my objects. There is no replacing IC by some local IC and needing to check things. It's just going to work very smoothly. The price you're paying there is that the tools you need to use are a little bit more complicated because we're going to move to optimal stochastic control. But it makes the problem much more amenable to computations and to like using it in actual applications. So that's really, for me, one of those cases where things in discrete time are great when they work, but it turns out that here they don't work very often. At least for moral hazard, it's a different story when you're doing this adverse selection I mentioned, but at least for moral hazard, and yeah, that's my opinion. Referees in econ journal disagree with me consistently that doing these things in continuous time should be accepted as usually being better, but yeah, like not everyone agrees with that. But you should, I mean, I should be able to convince you that basically when I'm here, I cannot do more. There are a couple of papers that try to do alternative things to this. There is a paper by Araujo and Moreira where they also put second order conditions, not just first order conditions, they add second order conditions there. You can do things, but again, it's not very general, and whatever you need to check in the end is a huge system that you don't know much, you don't really know much what to do with this. A couple of years ago, there were papers by Key and Ryan where they do what they call the sandwich approach, which something that's more general than the first order approach. It allows you to solve some cases where first order approach is not valid, but again, it's just like the level of generality you can reach with those, like the most state-of-the-art techniques there is very far from what you can do in continuous time. So it's just, yeah, like you need to invest a little bit of time understanding optimal control, and then you can do way more things than what's going on there. All right, but that's, yeah, that's going to be for this afternoon. Let me stop for now. Thank you.